This is an example of an enthalpy problem. To form glucose from carbon dioxide and water by photosynthesis, the reaction is 6 carbon dioxide gas molecules, 6 water molecules combined together to make one molecule of glucose, C6H12O6, and that's a solid, and it releases 6 oxygen gas molecules. You're asked to use the table below to calculate the enthalpy of the reaction under standard conditions and the enthalpy of reaction at 300 Kelvin, assuming that the heat capacity is constant. So the first thing we need to do is find the enthalpy of reaction under standard conditions, and for that we need the enthalpies of formation of the reactants and the products. The reactants are C6, CO2, water, and the products are glucose and oxygen. So to find the change, we need to take the sum of the products and subtract off the sum of the values for the reactants. And so it will look like this. We need the enthalpy of formation under standard conditions of C6H12O6, and we're going to add the enthalpy of formation for oxygen, and we're going to subtract off, and I need 6 enthalpies of formation for oxygen. I'm going to subtract off 6 enthalpies of formation for carbon dioxide and 6 enthalpies of formation for water. And I have to make sure I have the right values on the phases, otherwise I'm not going to get the right value. So here I'm going to substitute these numbers in. This is minus 1273.1. And I'm going to put the units all at the end so I don't have to worry about them here. I need 6 oxygens, and that value for the enthalpy of formation is 0 because oxygen gas under standard conditions is the standard condition, and for elements it's 0 in their standard state. I'm going to subtract off 6 times the enthalpy of formation of carbon dioxide and 6 enthalpies of formation of liquid water, and that's 285.0. And the units for this entire thing are in kilojoules per mole. Using my handy calculator, I know that this is 1273.1. Again, I'll put the units at the end. And I have to subtract off negative 2361.0 and 1714.8. This value here is negative 4075.8 kilojoules per mole, and I have to subtract a negative from a negative number. And so what I get in the end is 2802.7 kilojoules per mole, because subtracting a negative number changes it into a positive number. The second part of this enthalpy problem asks us to find the enthalpy of reaction at 330 Kelvin. In order to do that, I needed to know what the enthalpy of reaction was under standard conditions, which we did in the first part of this problem, and I have written that down here. It's 2,802.7 kilojoules per mole. In order to find out what the enthalpy of reaction is at the new temperature, I need to know how to adjust the enthalpy of reaction for a change in temperature. So we discovered earlier that the enthalpy of reaction under non-standard conditions is the enthalpy for the reaction under standard conditions plus the integral of the heat capacity times dt. And because this is a reaction, I can actually get the change for the reaction in the heat capacity times dt. And when I integrate that, that becomes the change for the reaction in the heat capacity times the change in the temperature. We already know this value. That's 2802.7 kilojoules per mole. And so now we have to find this. Let's start by finding the enthalpy, the heat capacity change for the reaction. And I have to do the same thing I did before. I have to take the values for the products, subtract the values of the reactants. And so the values for the products are 218.2, and the values here are joules per mole Kelvin. And I'm going to add in 6 times the value for oxygen, which is 29.4 joules per mole Kelvin. And I'm going to subtract off 6 carbon dioxides, which is 37.1 joules per mole Kelvin. And to that, I'm going to add 6 times the value for water, which is 75.3 joules per mole Kelvin. And so I need to get out my handy dandy calculator, and this is 218.2. I'm going to put the units at the very end just to save on writing. I'm going to add in 176.2 for the oxygen. I'm going to subtract off 6 times 37.1, which is actually 222.6. And to this subtracting off, I'm going to add 451.8. All of that is in joules per mole Kelvin. And that turns out to be equal to negative 279.8 joules per mole Kelvin. Now, in order to come back and actually get the enthalpy of reaction at 330 Kelvin, I first need the change in temperature. So my change in temperature is equal to 32 degrees Kelvin. Now that I've made myself some room, here's my enthalpy of reaction under standard conditions. Here's the reaction change in the heat capacity. Mine is 279.8 joules per mole Kelvin. And the change in temperature is 32 Kelvin. So when I multiply these two numbers out first, what I get is 8,953.6 joules per mole. Notice that the kelvins cancel. And I can't add joules to kilojoules, so I have to convert this number into kilojoules, and I know that there's 1 kilojoule for every 1,000 joules. And so this number becomes 8.9536 kilojoules per mole. And that number is negative. I forgot it from over here. And I subtract that from 8202.7 kilojoules per mole. And what I get in the end is 2793.7 kilojoules per mole. And I have to pay attention to my significant digits. So basically these don't really count. And that's the enthalpy of reaction at 330 Kelvin.